Okay. So today, actually, we are supposed to have done this lab last week, Friday, but because of the holiday, so we are doing it today. So it's lab 6 manual actually. So lab 6 manual, I think you have to attempt that yourself. I believe you have gone through that, but I will just try to. Oh, Mr. Naim, have you told them that already? Did I just move to lab 7?
Sorry.
Lab 6. The lab 6
no, lab 6 will be their assignment.
Yeah. So I don't need to talk about that, right?
Yes. You need to proceed with lab 7 only.
Okay. So this is lab 7. So I'm going to show you the manual. Sorry, guys. Okay, so we have lab 7 here. So basically, the objective of this lab is to look at how to implement k-nearest neighbor and support vector machine in Python. So this is the objective. And so we are going to be doing about, let me see, about 4 tasks. Yeah, about 3 broad tasks actually. So the first one is to look at how to use a simple, KNN for a simple example. So in this case, we are just using KNN on some data sets, right? So we're going to create the data set ourselves, X and Y, and then we are going to implement k-nearest neighbor. Then after that, we're going to build KNN on an established data set called Irish data set, and then we are going to look at how to work on that. Then after that, we are working on support vector machines. After the 2 examples on the k-nearest neighbor, we are moving to support vector machines, and we are going to look at the intuition of support vector machine. What is the advantage of support vector machine? What are the features and what are the use cases? So the use cases we are going to explore is what is the data set? Let me see. So we are going to work on Irish data set as well for the support vector machine, and then we are going to look at how we can tweak some parameters. So without wasting time, I'm going to show you my my notes, my notebook. This is my collab notebook. So I try to let me just clear the output in case I have done anything here. Clear output. Okay. So now for the first case is to use a KNN neighbor for a simple classification task. So to do that, we import numpy as np. Then since we are using classification, right, we are going to use k-neighbors classifier model, because you see k-nearest neighbor itself can be used for classification and then regression. It's a machine learning model for both classification and for regression. But because we want to use it for classification in this case, we are using k-neighbors classifier. For regression, I think it is k-neighbors regression. So that's why we call this from sklearn.neighbor. Let me see. For the regression, let me show you from where are you going? From sklearn.neighbors. Import k-neighbors regression, I think. Okay, so this is for regression and this is for classification, right? more about it in this for this classifier. You can read more about it from this web page in scikit-learn. So yeah, if you go there, you see some examples where they use k-nearest neighbor classifier for classifier comparison and all of other things. Yeah, so you can check that. But basically, what it's basically doing is that when you want to use it, just call it, and then there are some things you are going to pass to the model, like the main n neighbors, because the idea of k-nearest neighbor is that it classifies the data set based on the number of classes that fall in a selected neighbor. For instance, if you have like a group of data sets and then you select n neighbors to be 5. What you are saying is that for the classification of the data set, it should consider the 5 nearest neighbor to each of the points. Let's say you have 10 points that you want to classify, and then you want to train the data set based on k nearest neighbor, and you put n neighbors to be 5. What it's saying is that for point 1, look at 5 points that are closest to the point 1, and then consider their classes. So let's say out of the 5 points that are closest to point 1, 3 points is class 0, and 2 other points is class 1. Then, because you have more points belonging to class 0, then that point will be classified as class 0. So this is how k-nearest neighbor works, basically, right? So you can read more on that here. So I'm just going to share the link for the k-nearest neighbor so that you can, if you want to read more about it. Why is this thing not sorry guys, where is the message option here? Oh my. Anyways, just if you check that, I can't find the message option on this, and I don't know what's wrong with my so that's the documentation. Okay, now let's proceed. X, we created we created n array of this data set, and then we reshape it to be -1, 1. You know, I told you about the function of reshaping is just to make your data set to be 2-dimensional, right? Because we have 3,000, 1,000 here now, so we call it -1, 1. Then our Y array, which is the classes corresponding to this data set, are this. So then we created X text and Y text. So we call our model. Model here is k-nearest neighbor classifier. The number of neighbor we pass here is 2. So we pass number of neighbor here to be 2 instead of the default 5. If we don't put anything there, remember the default here is what? Is 5. So if you consider that the number of neighbor is 5, but here we just change it to 2. So you can explore which of the parameters will give you the best performance, because if you change the parameters, you're going to have different performance. So after that, we fit our model on our training data sets, which is the X and Y, and then we now predict with our test data set, right? So just call the model.predict XX, then you now print Y predict, right? Let's run that and see what we have. So it's running, and then let's see. Okay, so this is the nearest neighbor link. You can check it here. So you have the classification, you have the regression here. So if you want to use regression, you check this. If you want to use classification, you check this. And then k-nearest neighbor is also used for unsupervised classification also. I mean, we have not gotten there. Maybe we are still going to talk about unsupervised classification. So this is for regression. So you can use this one for the regression. You know, you have nearest neighbors and then nearest neighbors. So just check the documentation anyways. Okay, so we have our prediction here. This is 01110, but then remember our true data is the y test, right? Because we predict for the x test. So if we compare for the y test, you can see that this one has just one of the values predicted wrongly, like the last one is 1, but it predicted 0. So if you want to check further, you can find the score of your model. Just call model.score. Yeah, model.score. So we want to score the x text, right? And then y text. Let's see, it should be 0.8, I think. Yeah, 0.8, because you know from your values here you can see that 4 values are predicted correctly. So out of 5, so that's 0.8. So that's the KNN simple use case. So let me delete this. Okay, I have this one here. Okay, so let's look at the next one. Is to build KNN algorithm with iris dataset. Iris dataset, basically it's a data set of iris flower. So iris flower, you know, I want to show you. So what we want to do here is just to show you what iris flower looks like. So to show you an image, you are going to use CV2 packages. So to use CV2 packages, we just import it, right? Import CV2 underscore imshow. This imshow is like image show, to show images, right? Okay, so we read the data set content.iris example. For me to read it, I have to load the data set. So I'm going to load the data set. I mean that image. Where do I have it? I have it somewhere around here. This is it. Right. Okay. So I just put it there. That's the content iris example. Then I just show it, CV2 im show, and I ask it to resize to 400 by 150 pixel. So it will just show the image basically. So you have the image here, and then if I go to my what's it called? If I go to my anyways, so this is the image. Now what we want to do is, remember the idea of this section is to use k-nearest neighbor on this iris data set. So you have to understand what is the iris data set. This is it actually, but what are the parameters? The parameters are actually some measurement of this iris data set. Like what they did basically is a research work. They tried to collect different species of iris data sets, about 3 species, I think, 3 or 4. I mean, it's 4. So they collected 4 different species of iris data sets. I mean, different numbers, like maybe for, I think, 50-50 for each species. So that means if you have 4 species, you have about 200 records or 200 samples now. So what they did is that for each species or for each sample, they measured some parameters, like they measured the sepal length and the sepal width and the petal length and the petal width. So these are the features of the iris data set. So for each of the species, they measure these parameters and then they now put their classes. Okay, if this one is 20 centimeter, this is 0.1 centimeter, and this, then we know that this is maybe Setosa species. Okay, so this is what we want to do. We want to use k-nearest neighbor to classify the data set, right? I mean, to classify the iris data set based on their parameters. So we just import NumPy, then we now read the data set. This is iris.csv, right? I'm going to load it again using import on my session storage. So I have it here. Iris dataset. Where is it? Okay, I have it inside here. Okay, so I have it already here, iris.csv. So I'm just going to run this now. So I print dataset.shape, right? So you can see it is 150 by 6. Okay, 150. It is actually 3 classes, not 4. It is 3 classes and 50 examples for each of the classes. So that's why we have 150 records here. And you have six columns. 6 columns, you know, we're going to see what the columns are actually. So the total number of sample is 150. So let's see dataset.columns now to see the number of columns, and then we want to find out the species, right? So we have sepal length, sepal width, petal length, petal width, and the species are 3, you know, Setosa, versicolor, and Virginica. Let's look at what that data set looks like in a table, right? This is it. You see, we have, according to our dimension or our shape values, we have 6 columns, which is ID, this, and the species. So this is the iris data set, right? So what we want to do is that we want to, you know, most of the times before you even start any machine learning modeling or something, you actually want to like see how your data sets are distributed, how your variables are distributed, right? So one very good plot that you can use is a pair plot, right? You can use it to see the distribution of your variables, right? Because like somebody sent me a mail last week to ask that I think it's from the other class that she wants to use a machine learning model for one data set, but she's not sure if she should use linear discriminant analysis or quadratic discriminant analysis, right? So yeah, how can she determine the best of the models to use among the two? You know, one thing is the way to go about it is that you can know that, you know, LDA is a linear model. It actually fits a, you know, QDA can still find curve, you know, a quadratic curve to use to classify your data set. So one way to know if you can use LDA perfectly or QDA is to use pair plot. You want to see the plot of your data. If it's a linearly separated data, I mean linearly separable data, then you can use LDA. So let's just run this and see what I'm saying. So to do that, we use pair plot, but this pair plot method is under Seaborn, right? Seaborn is another plotting package in addition to Matplotlib. So it's actually a method inside Seaborn module. So I just call sns.pairplot. Then I pass my data set. Remember, my data set is this iris data set, right? And then I drop the ID column because the ID column is not necessary for us to plot. It is just the ID. So I just drop the ID column. Then here I specify that my HUE is species. You see, this HUE, what it does is that it is used for the symbology, that when I plot the data, how should I symbolize the data set? You can see that if you check the symbology now, it is symbolized based on the species, right? We have 3 species, and each of the species are symbolized on different colors and then shape. Like the Setosa is blue circle, the versicolor is orange rectangle or square, the Virginica is this, right? So this is it. We have our plot here. What can we get from our plot? You can see that, you know, you can almost use linear something for the separation of this. Like a linear line can separate this blue and then the other 2 classes, right? You can use linear line here. Okay, let me just explain this pair plot first. You see, this pair plot, what it does is that for each of the variables or for each of the features of your data set, is going to plot against another one. It's going to plot each feature of your data set against another feature. For instance, look at this sepal length in this y-axis. It is plotted against sepal itself first, right? It tries to plot sepal length against sepal length, but then it plots after that sepal length against sepal width, against petal length, and against petal width. Now, this plotting against sepal length is just not going to give you the plot because it's not actually possible to plot something against itself, right? So what it's going to do instead is it's going to give you the distribution of the other data set, this other three, right? So if you move to the next one now, you can now plot SEPA length against SEPA width, and then SEPA length against what's it called, the other two, and all of that. So this is the plots for the peer plot. So you can see, look at it. The SEPA length, which one is this? The Setosa, you can see the Setosa class is linearly separable from the other two classes, right? The versicolor and the Virginica. Actually, you can separate it, right? You can separate this, what's it called? The Setosa from the other two classes. But then, if you look at the versicolor and Virginica, you can see that they overlap. So you cannot use linear line to separate these two classes, right? So that means you have to use a more adaptable model. Okay. So let's look at how to prepare our data now. To prepare our data, what are the data preparation activities or tasks that we have to do for most machine learning models? The first one is standard scalar. You know, standard scalar, I think this is the first time we are talking about standard scalar, is one important and very vital activity in machine learning or task in machine learning. So what is standard scalar? Standard scalar is a way of bringing your data set into the same scale. Because imagine you have one data, let's say for instance now, you have age record, right? And you have one person is, one of the data sets, you have the age for a baby, like maybe 2 months or just 1 year. And you have like another one person that is as old as 70. You know, the scale is not really good for your data set. It's going to make your data set it's going to affect the performance of your data set, right? And it's going to affect the time it takes your data set to train. So it's good to always, bring your data set to the same scale. So one way to do it is to make it maybe to range from 0 to 1, right? Or to range to have a standard deviation. So here, what we are doing basically is to use standard scalar. So to do that, we just import standard scalar from the preprocessing package, right? And then after that, we want to, we want to split our data set. So splitting the data set, is just to have some set of data for the training and the other set for the testing of your data. So to do this, I think you have used this package before, but remember the one we have been using most in the past classes or the past labs is the indexing, right? We have been using indexing whereby we just say training is from 0 to maybe 100, then but here we want to just use train test split. That's why we import this train test split, right? So one other thing to use is label encoder. Why do we need this label encoder? We want to use this label encoder because in our data sets we have I'm not sure we use label encoder here. Okay, so we are not using label encoder for now on this data set, but we are still going to use it later, right? Okay. Because remember, we have the reason why we are using label encoder is because if you look at the species here, we have 3 classes, and then they are in strings. This is Setosa, this is Virginica, this is this. But for our model to understand, we have to put it in terms of distinct numbers or something. So let's say we want Setosa to be 0, we want the second class to be 1, and the third class to be 2. So that's why we use label encoder. It's just to encode our species classes, just like the way we did for the age feature the other time, where we have male to be equals to 0 and female to be 1. So the same way we want to do for this species also. Okay, so so that's why we use all these 3 packages. So here I'll just run this. Now let's look at something now. Feature columns is just to define our features, right? Because we have 4 features, so that's why we put feature columns here. So this data set, we are just getting the values of the feature columns out of the data set here. Let's print our Y. Remember, our Y is the species and the value, so we have it there. Now let's use label encoder first, so which is what to change this Y into classifiable numbers or something, 0, 1, 2. How do we do that? We just call label encoder, we initiate label encoder, then we fit transform our Y, right? So fit transform Y on the label encoder. So we have it to be like this: 0 for the first class, 1 for the second class, and the 2 for the third class. Okay, so how do we use the train test split? To use train test split, we have to pass in our data set, which is the X for the training, Y for the testing. Which is the X for the what's called features, and then the Y for the targets, features and targets, right? So what it's going to do here is that since we pass X, it's going to split X into X train and X text, and also we pass Y, and it's going to split Y into Y train and Y test. Then how does this method, how does it know the size of splitting? So we can pass the text size to be 0.2. What we are saying here is that, make the text size to be 20% of the whole data set. That means text size will be 20%, and then the training size will now be what? 80%. You can specify, instead of the text size, you can specify the training size here. Just call this one training size to be 0.8. Then you know that the text size will now be 0.2. So I'll run that now. So we have that. Let's look at the effect of that. Let me call X train. I'll just print, let me print X dot shape, right? And then I'll print X train dot shape. I'll print X underscore test dot shape. Okay, so we just print that. So we see our X, our data set as a whole is 150 by 2. Then why it is by 2? Because we specify here that we want the features to be separ length and the petal length, not all the 4 features here, right? So that's why we have by 2. Then our X train is now 120 by 2, because 80% of 150 is going to give you 120, right? Then our text shape is just 30 by 2, because that's 2 of 150, or 20% of 150. Okay, so remember we have performed 2 pre-processing now. The first one is label encoder to change the targets into labels, encode it into different classifiable labels, and then we did the train test split now to split our data set into training and testing. Then the next one is to use standard scalar, right? And I explained standard scalar that it is to scale the data. Okay, how do we do that? To use standard scalar, you just call the standard scalar method that you have imported, and then you now use the fit, which is for it to learn on your data set. You call the fit method on the standard scalar basically. Now, you see, standard scalar application is in 2 phases. The first phase is where you train your standard scalar on your data set. Then the second stage is when you now eventually transform your data set with your standard scalar. So this is where we train it. Now this is where we now transform the data set. So the transformation is like the conversion eventually. The training is the learning, because standard scalar is for you to convert, right? But then it has to understand what is the variation in the data set so that I can now bring it back to another scale. So these are in two phases, the training and then the transformation. So now we want to transform now. So when we transform our data now, you can see we transform the train and we transform the test. Now look at the variation or the scale of the data set. You can see it's between -1 and 1 or something. So what this standard scalar is doing is it makes the data set to have a mean of 0 and the standard deviation of 1, right? It has a mean of 0 and the standard deviation of 1. So compare this to initial data set that we have. I think where is that? You see now 3.5, 1.4, it varies. But here we have some, some data set that now conforms to some scale. Okay, so that's that. So now we can when we are done with that, we can combine our data back. So the combination of the data is that, we have scaled the X train and the X text differently. So we want to combine it together again to now have one single data. So just use np.pstack X train and X text, and also np.hstack Y train and then Y test. So when we combine the data, okay. Now let's use KNN algorithm. It's still the same way. We just import K-neighbors classifier here. We initiate our K to be 6 instead of the default value of. Then we just now call the neighbor, and then let me run this and fit. Now we fit the what's it called? The model with our train and the Y train, X train and the Y train, right? Then now let's look at the accuracy of our model. Now the accuracy of our classifier now on the what's it called? Now remember, look up guys. We find the accuracy of our model on the training data set. So we have 0.95. And the second line, we find the accuracy of our model on the text data set. We have 0.93. So this is the performance, how well the model performs on our data set. So do you have any questions? So we are done with k-nearest neighbor. So we're going to move to what's it called? We're going to move to the next, which is support vector machine. So, but before we proceed, do you guys have any questions that you want to ask? Do you have any question, guys?
So far, no, sir.
Okay, so we just proceed. Okay. Okay, now we'll move to support vector machine. Just close this. Okay, so support vector machine. What is the intuition behind the use of support vector machine? You have to understand why support vector machine might be the right model for you to use compared to the other models we have been exploring in the past. Okay, so that's what we want to do now. Let's import our necessary packages, right? Let's import seedborn. We want to generate some random data sets, right? sklearn has a feature called data set. It's actually a module called this data set. Inside the data set, you have so many options for you to create data you want to work with and maybe explore, right? Like all the data sets we have been downloading in Excel or something, you can easily import them from sklearn data set. They have almost all of them, like the housing data set, the IX data set that we used from that we imported as CSV, sklearn as it. Like just I'm telling you this just for you to be so resourceful with machine learning. Sklearn data set, because you know data is an important thing in machine learning. So you can see we have load iris data set, you have the load wine, you have the Boston housing data set, you have the diabetes data set, so many data sets for classification and for regression. So you can explore, you can lay your hands on it, and then you can work on most of them, right? So like now you have the toy data set, Boston housing data set, iris data set, and like you see in the previous work, it's also 150, 50 in each of the three classes. So you can look at it, and there's more detail because you have documentation here. Instead of just getting the Excel or the CSV, you can read about the documentation. You can get to know about the distribution and a lot. The diabetes data set, handwritten data set. You can just check all of the data set here. So there's one. The reason why I'm showing you this is to explain something. We can generate data set also, right? Let's see, generate data set. Toy data set, I think. Generate data sets. Make blobs and is that I'm looking for something else. Okay, I can't find it. Okay, this is it. I think this is it. Make circles. Okay. Okay, this is generated data set. What this generated data set is actually doing is that, depending on the kind of problem you want to explore, you can generate different data set yourself. You can generate blobs, you can generate classification data set, you can generate circle data set, right? And you can generate kind of like Mons data set. Okay, so what we are doing here is we want to generate blobs. You see, this make blobs data set is actually a classification data set. What it does is that it's going to give us a sample of data set. Depending on the number of samples we give, here we give it to be 50, right? And the data set will be features and the targets, right? That's why we put it X, Y. X to be features and Y to be targets. So by default, right, the number of class, let me just click that for you to see. By default, the number of classes is going to be 2. I mean, the number of features is going to be 2 by default, and the number of class, I think, is also going to be 2 by default, right? So basically, you have, when I call this, that means I have 50 features, 50 samples, and then 2 features. That's what I generated here. If I use this, right? Then let me look at my shape. You can see 50 by 2. If I change this one to maybe 70 now or 100 now, if I change 100, I'm going to have 100 by 2, right? Now, let's look at my X. What does it look like? I'm going to change it back to 50. Right. Now, let me look at my X. It's just some random generated data, right? 50X. You can see I have samples, 50 records by 2 features, 50 samples rather by 2 features. Now, my Y is going to be the target, and that's going to be 50 also, but we have 2 classes, right? So that's going to be 50. You can find the shape, find the shape, right? 50 by 1, you see, 50 by 1. Okay, now let's plot the data, just the scatter plot. You can see this is the distribution of the data, right? How did I plot the data? I just called scatter method on the plot, and then I pass the first feature and the second feature. So this first feature is X of the rows, this all the rows, and then the column is 0 now. right? And the second is all the rows, and this column is 1, okay? So I can plot like maybe just 20 of the features, just for you to see 0 to 20 here, and just 20, you see, because that's with X. Okay. It's not consistent with X, so I have to just yeah, that's true, because our Y is 50, so I'll just leave it like that. Or otherwise, I change the dimension of the Y. Okay, that's the plot basically. So why are we doing this? The reason why I'm doing this is that I want to show you some intuition. If I want to use linear classification for this problem, I can easily do that, right? I'll just fit a line here. I'll just find the best line to classify this thing. But one issue is that, look at this distribution. I can fit a line like this, right? I can make a line go like this, just pass through, what is it called? Oh, just pass through like this, and then it will classify the problem. I mean, it will classify the data set perfectly. Or I can make it go like this, and it is also going to classify the problem good. Or another one come like this, and it's going to do the right classification also. But now the problem is that for the different classification that I have, I'm going to have most likely different prediction for the same data. Let's look at example of what I mean. Let's look at this example. These are the 3 different lines that I can use to classify my data set. This one line classify well, this one classify well, this third line classify well. Now let's say I have a data set X here, this X. If I want to classify this X based on the first line here, this first line here that passed through 3, the first line, where do you think X will be classified? Is it going to be red or yellow? This X line, X point, is it going to be red or yellow? And this one should put later. If I want to use just this one, ignore these 2 other lines. Imagine these 2 other lines are not there. If I have just this one line there, and then based on this one line, I want to classify this X as red or yellow, where do you think this X is going to be classified? Somebody should talk.
Yellow.
Yeah, it's going to be yellow because it's now falling on the yellow side of the line. Okay. Now, if I use the second line here, this middle line here, and I want to classify this X, you see, now X is now falling on the red side of the line. This is now going to be classified. Sorry, I need to work this Windows license. It's now going to be classified as red, right? Okay. Then if I use the third line also, this one is also going to classify it as red. So the point is that there are more than, there are more than 3 lines, or there are more than 1 line actually that classify this data set. How do we determine the best line of fit to be used? That is what support vector machine is used for. Support vector machine tries to look at a concept to select the best classifier for your data set. So what is the concept? The concept is, instead of just drawing one thin line, right? You can see, rather than simply drawing a 0 width line between the classes, we can draw around each line a margin of some width up to the nearest point. So what we are saying is that for this one line, we are going to draw a margin up to this nearest red point, and then a margin up to the nearest yellow line. So that means the margin for this one will be to here, and for this one will be to this point. And also for the middle line, the margin will be to this, this is the middle line, and for the middle line, this is the nearest point. So the margin will be from this middle line to this nearest point, and then the margin to the yellow class will be from this middle line to this, this is the nearest point of the middle line, I think. Yeah. And also for the last line, we draw margins. So basically what we are doing is that we are looking at, out of those 3 lines, which of them has the largest buffer, right? The largest margin. So the best line to be selected is the one with what? the largest margin. So that's what support vector machine is basically doing. That's the intuition of support vector machine. Support vector machine is creating hyperplanes. Now you can consider that margins as what we call hyperplanes. You know, the hyperplanes for the red line and the hyperplane for what? The yellow line. So he's looking at it that among the three lines, or among all the possible lines that I can use for my model or for my classification, which of them has the best, the largest hyperplane? So the one that has the largest hyperplane is the one to be selected, right? So you can see, this is, like I explained to you, this is the margin for the first line, this is the margin for the middle line, and then you can see the middle line margin is from this to this, and then this. Now from here, we can now say that the best line of fit is this middle line because it has the largest width, right? So that's the idea. The line that maximizes this margin is the one we will choose as the optimal model. So support vector machines are an example of such a maximum marginal estimator. Okay, so let's look at the application of support vector machines in real data set now. To do that, we are going to import, because we are doing classification tasks, right? We are going to import SVC, support vector classification, from sklearn.svm. SVM is the support vector machine generally, right? But SVM can be used for classification and regression. That's why inside SVM, we have SVC and we also have SVR for support vector regression. So here we are using SVC, okay? So then we now specify the kernel to be linear. Linear kernel is used just like, we see this is a linearly separable data. So that's why we use linear kernel, right? You can change the kernel. We have different other kernels that you can use. You can read more about support vector classifier, or let's say support vector machine, scikit-learn, right? Scikit-learn is always a very go-to resource for your machine learning with Python. So, you have SVC, and then you can look at the kernel. This is for the linear kernel. You can see linear kernel is used for linearly separable data. And then you have some other kernel like the RBF kernel, which is used for some more complex distributed data. And then you have another polynomial degree 3 or something. So based on the distribution, you can change the kernel types. So you can read this up for your support vector machine, right? Okay, so we just fit our data X and Y, right? And our X, remember our X and Y are the generated data set. So you just want to plot this. Now, what the reason for this code is for us to plot the hyperplanes for our support vector machine. So we see how it works. Now let's look at this. Then for the same data set, you can see this is line, and this is our support vectors, right? These are our support vectors for the red line, support vectors for the yellow line. So we can also paint it in terms of numbers, and we have it, yes, right? So so let's look at the kernel. Remember, I talked about kernel just now, like the type of kernel we can use, the linear or the other types. So this is the intuition of that. I think I've just explained that, but just to show you the example. Kernel tweak. How can we tweak our kernel? Now, okay. Now we want to look at another example of data set that is not linearly separable, and then assess or explore the influence of kernel parameter on our support vector machine model. So to do that, instead of using make blobs that we used initially, we are going to use make circles, because we want our data set to be in form of circle, right? Or in form of circular distributed data set. So we just X, Y, and we make circle, we call it 100, that is 100 records or 100 samples, right? Now, let's look at a sample model of support vector classifier created with a linear kernel and fitted on our data set, right? We call it CLF classifier. Now let's plot our data set and our classifier now. Now you see, this is a secular distributed data set. And because we use kernel to be linear, this is the best line that it can fit, right? But then this is not this is not a good model at all, because it's not even doing the classification, it's just fitting the line. And these are the hyperplanes, you know. This is the hyperplanes of the yellow line, and this is the hyperplane of the what's it called, red line. So this is not the right one. Kernel linear is not perfect for this work. So how can we do it? Okay, let's look at the 3D distribution of the data set. You can see this is how the data set is displayed in 3D. Now, this is the kernel tweak. A simple way to work around this problem is first change your kernel from linear to, you know, like I show you. You check the kernel something. You can use RBF now. So you know RBF is able to, you know, be circular in shape, and then you can use maybe polynomial 3 or something also. But let's just use kernel to be RBF. So now we created another CLF. Now we put the kernel to be RBF, then we feed, and then we now plot. Now you can see what happened. By changing the kernel to be RBF, we have a new model that is able to, you know, be fitted according to the distribution of your data or your sample data. So you have it in circular form now. You have the hyperplane and you have the other outer hyperplanes now. So this is your new distribution. I mean, this is your new model that perfectly classify your data samples. Okay. So one last thing that you want to do is, you know, in situations where you have some what is it called, overlapping data, like you have red that is going on top of the yellow and all of that, what you can do is you can change the, what is it called, what's the values here, yeah, the C. I want you to explore what is the influence of changing C for your support vector classification. What C will do basically is it will make your model to effectively know how to tweak around overlapping data samples. I want you to go and look at the influence of softening this margin. The margin is called C. So explore and change the values of this C for these data samples, this one that are overlapping, and see what you have for that. So let's check our this thing and see how far we have gone. Okay, so the last one for you to just check is softening the margin. So from here, we have been able to go through all the tasks of this thing. We have looked at kernel tweak, changing your kernel from RBF to, from linear to RBF, and then the SVM kernel, linear, and all of these. I've done all of these things. So basically, this is the demonstration for this class. So do you guys have any question now? Yeah, through with the class. Any questions from you guys? Any question, guys? Before I unshare my screen. Do you have any question? Okay, so since there is no question, we're just going to Mr. Naim, I pass the class to you.
Okay. Thank you, Mr. Nahim.
You're welcome.
Thank you very much.
You're welcome, sir.
Okay. So since you all have no questions, so can we dismiss our class, everyone? Hello.
All right, sir.
Okay, good. Thank you very much. See you this Thursday, 4 to 6. Don't forget the lab eat. Thank you. Bye. Assalamualaikum.
Thank you.
Mr. Naim.
Waalaikumsalam.
Yes, Mr. Nahim.
Yeah, so subsequent classes, when are we holding the subsequent classes? Is it on Friday?
No, Thursday. Since this Friday is also public holiday. So
I see.
for our lab 8, we will do concurrently with your ME2G1 group.
Oh, okay. That's
Is it okay for
Okay.
you?
Yeah. Miss City told me yesterday, so that's fine.
Okay. Because this Friday is our public holiday.
So many holidays, you know.
Okay. Thank you.
Okay. Yeah.
Thank
Bye.
you. Sorry. Assalamualaikum. Bye.
Waalaikumsalam. Bye.